We can also show the inverse of a linear transformation using these two different linear transformations here. We know that these two are linear transformations from R2 to R2. It's because we have two components of our here in our domain, and this will be two components as well of our codomain. Same thing with here and here as well. Now, to show the inverse of a linear transformation, we need to structure this process. First, come up with the standard matrix of the linear transformation. Then, make sure to find the inverse of the standard matrix. If there exists in an inverse, then our linear transformation of T is invertible. If ever our inverse is not there or not around, or it's not invertible, automatically our linear transformation of T is also not invertible. But if it did, we're going to multiply it with a certain vector, and we're going to talk about it later if it's possible, and then we could come up with a statement of our inverse of our linear transformation. By the way, it's inverse. Okay, so to start with, let's come up with the standard matrix of our given transformation. You have here x and y, so all the coefficients of x will be in one column and y will be second column. Our first here is x plus y. So you have here 1x plus 1y. That's your first entries. And we have here 3x plus 3y. So 3 and 3. This is not the correct form because we know that our domain is on R2. So we have two columns as mentioned here. Now, for some of you who can analyze this carefully, look at the two rows. Our second row is a multiple of the first row. So there, by stating that, we expect a row of zeros if we talk about reduced row echelon form. And if we have rows of zeros, then that means our determinant is 0, and hence our matrix A is not invertible. The answer here should not be invertible. But of course, if you have missed that analysis, we can solve the inverse of our standard matrix following this. Since this is a 2 by 2 matrix, we're going to use this as part of the theorem we've learned before. Okay. In this process, we can come up with the inverse of our matrix A, where our A is equal to 1, B is 1, C is 3, and D is also 3. To start with, we need to show the value of this, which is considered to be our determinant of a 2 by 2 matrix. You have here A is 1 times D, which is 3, minus our B, 1 times our C, which is also 3. We have here 3 minus 3. In short, our determinant is 0. As mentioned, if our determinant is 0, this entire expression will be undefined. In short, our inverse of A is non-existent. Hence, A here is not invertible. And if that would be the case, we are going to cut short all of these steps here because A is not invertible. And automatically, we could say that T is also not invertible. Just like what the analysis mentioned earlier, we have here columns which are multiple of the other. Hence, one row would be zeros. And if we have 0 rows, then the determinant is 0. Hence, the matrix is non-invertible. Same here, T is not invertible. So let's see if our second transformation has an inverse. So again, our matrix A here, standard matrix, we have 1 plus 4. Then we have here 1 and negative 4. To get the inverse of this, or to check whether there is an inverse, we'll have here this form. Solving for our A is 1, B is 4, C is 1, D is negative 4. So AD minus BC can be solved as 1 times negative 4 minus 4 times 1. You will have here negative 4 minus 4, negative 8. So AD minus BC, our determinant is negative 8. Hence, we can show now the result of our inverse of A. We have 1 over negative 8 times your D as your first entry now, negative 4. The negative of 4 here negative 1, and positive 1 here. Okay, so when you have that, your inverse now is negative times negative is positive 4/8 or positive 1/2. Positive 1/2 here as well. Positive 1/8 here, and you have negative 1/8 here. This is the inverse of our standard matrix A. And just by this, we have equivalent statements that if our standard matrix is invertible, that automatically our T is invertible. And since our goal here is to solve for the inverse, let's continue this and use that inverse multiplied with certain vector V. Our vector V here has components x and y, as this is the part of our domain. This means we have here 1/2, 1/2, 1/8, negative 1/8 times x, y. Okay, so with this, we can now multiply this. 1/2 times x is 1/2 x. Okay, that's your first entry. Take note, this is a 2 by 2 matrix, 2 by 1, so your result is a 2 by 1 matrix. So you have plus 1/2 of y. That's just one entry. 1/8 x minus 1/8 of y. This is 2 by 1. 2 rows by 1 column. This means that the inverse of our linear transformation xy is denoted by these two entries, 1/2 of x plus 1/2 of y, then 1/8 of x minus 1/8 of y. Factoring out 1/2, so you have your inverse of the linear transformation T being x plus y over 2 and x minus y over, not 4, over 8. This is the inverse of the linear transformation T described as this. Okay, we see that one has an inverse but the other is not invertible. Thank you very much for watching.